Welcome everybody to the GRASP SFI seminar. Today we are pleased to be joined by Anthony Rowe. Anthony Rowe is the Daniel and Karen Walker Pseudo Professor in the Electrical and Computer Engineering Department at Carnegie Mellon University. His research interests are in network real-time embedded systems with focus on wireless communication. His most recent projects have related to large-scale sensing for critical infrastructure monitoring, indoor localization, building energy efficiency, and technologies for microgrids. His past work has led to dozens of hardware and software systems deployed in industry, 5 Best Paper Awards, and several widely adopted open source research platforms. He earned a PhD in electrical and computer engineering from CMU in 2010. Received the Jilton Luton Joel and Spira Excellence in Teaching Award in 2015, the CMU CIT Early Career Fellowship, and the Stevens Ferris Award for Systems Research in 2015, and the William D. and Nancy W. Strecker Early Career Chair in 2016. With that, we give you Anthony Rowe.
Cool. Thanks for the introduction, Carl, and thanks for the invitation to talk to your group. I definitely I know a fair bit about some of the work that the GRASP Lab has done in the past, and through some of my connections actually with VJ during the TerraSwarm SRC Center. So maybe that was before many of your time. But today I'm going to talk a little bit about some of the new work that my group has been doing as part of a larger research center, this CONIX Research Center, which is again a semiconductor research corporation sponsored sort of multi-university project. So before I sort of dive into it, I wanted to talk a little bit about my background. So I'm a professor in electrical and computer engineering. My background is really in embedded sensing systems. So I've done a fair bit of work in the past in wireless communication. So these are kind of some pictures of low power, wide area networking towers that we've deployed on campus. So LPWAN or LoRa, for those that are familiar with it. We've taken some of these technologies and actually commercialized them for things like smart metering systems. My lab tends to build a lot of sort of board level hardware, like sensing devices like these. And over the years, that kind of got us in the direction of looking at GPS denied indoor localization. And we'd been building sort of modules that you could install on first responders or firefighters or workers in, things like this oil refinery to do tracking for safety purposes. And that sort of journey through sensing and communication that led into localization eventually kind of opened up the opportunity to work on sort of mixed reality and spatial computing. And so I'll be talking a bit about that today. As I mentioned at the beginning, a lot of this is a project that's sort of a subcomponent of this CONIX Research Center. And here's kind of the list of universities that are involved in that. So a lot of the work that you're going to see today is actually a collaboration across all of these different universities. And I'll try to highlight, different PIs that are working on particular subcomponents of it. I tried to pick a selection that I thought might be more relevant to sort of a robotics community. We'll see if that that actually worked out. But please feel free at any point, if you guys have questions, just interrupt. I'll try to monitor the chat, although I've got a lot going on with multiple screens right now. So hopefully maybe Carl can also just, if somebody asks a question, just feel free to interrupt. So to get started, I wanted to make sure we were all on the same page. I realize many of you probably know about mixed reality, but may not actually be experts in that space. So when people are talking about mixed reality, they're really talking about ways to project digital content into the physical world in a way that looks sort of realistic and natural. There's a bunch of different modalities for how you might do that. So on the left here, we see kind of an example of an IKEA Placeware app where you're using what's called mobile augmented reality. You're looking through a tablet that's sort of being tracked in 6 degrees of freedom to project an image in the space, all the way to things like, Hololens headsets. There's also a lot of terminology abuse in sort of the mixed reality space. I wanted to just quickly talk about the different terms and what they actually mean. So virtual reality is the obvious one. It's kind of the helmet that blocks everything out. Augmented reality, if you think about it, if you talk to many experts, they would say it's actually just a heads-up display where you're putting content in a user's field of view, but that content doesn't necessarily interact with the physical world. So kind of Google Glass, I think, would be an example of augmented reality. Mixed reality is really where you actually have that overlay of content, that augmented reality content that's linked in with the physical world. And so that requires you to track your head position in 6 degrees of freedom to overlay the information accurately on the scene. So here you can kind of see people interacting with construction equipment that, as they move around, it stays fixed and it's annotating these, in this case, pipes. And then people have kind of just started to use this word experience reality as just a general catch-all for all of these things. And sort of a nice example of this is kind of a video that shows something called the North Star, which is from Leap Motion. I kind of like this example because this is an open source, freely available XR platform, one of the few, where you basically have a display that's mounted sort of in front of the user's forehead that's going down into a semi-reflective lens that's allowing it to overlay the content. And then they're using hand tracking inside out from the headset to actually do the tracking, the manipulation, and the occlusion that you're seeing in the video. So this is really kind of a nice example of proper mixed reality. I want to just quickly talk about sort of the background and the history of where all of this came from. It actually started as early as 1968 with Ivan Sutherland creating this sort of almost completely analog only augmented reality system. He had an acoustic tracker for a headset, was able to display some vector graphics there. It was pretty especially impressive for the time. Took us many decades to actually catch up with that. In the early 80s, thanks to a lot of the work in the robotics community, we started to see, people thinking about and manipulating 3D point clouds. Of course, in 1984, we had the Terminator, which, hopefully, thanks to the robotics community, won't happen. I'm hoping you guys don't actually make killer robots. But this was kind of one of the first examples from Hollywood where people could actually see proper mixed reality, where you had an overlay that was fused in with the environment. Whole bunch of other things. 1990, sort of Boeing engineers coined the term augmented reality. In 1992, you had a seminal paper on sort of the continuum of reality, which is when the academic community really started to think about augmented and mixed reality problems. Late 90s, we started to get good at real-time SLAM. We had a flurry of, activity in the mobile space, Google Tango, a bunch of better depth sensors. 2016, we had Microsoft HoloLens, which is kind of the first commercial product that hit. And then in 2017, this was kind of really a pivotal point where ARKit and ARCore came out, which were sort of these mobile platforms that allowed you to do mixed reality development. And this kind of commoditized that whole space. And then in 2018, we had, a flurry of Magic Leap, Teleportation demos from Microsoft, a whole bunch of stuff happened. And then, of course, just a few weeks ago, we have the big news that Facebook is actually changing its name to Meta. They're sort of going all in on mixed reality and this notion of the metaverse. So I kind of want to step back and say, okay, hype, or is there actually substance to it? I'd argue, given the long lineage we have even within the research community, that there in fact is a lot of substance. I don't know if Facebook's sort of big media push is actually going to help or hurt the community. It certainly has put it in the spotlight, at least recently. The interest that I have in mixed reality is much more about connecting mixed reality systems with sort of machinery and industrial automation backends. So if you imagine sort of mixed reality and Internet of Things, and I think there's a whole bunch of sort of interesting application spaces where that comes into play. These are examples where you can see people who are being virtually coached by compute systems. So you can imagine like doing repair tasks on cars. This was actually kind of the original Boeing vision. Boeing was working on this to actually help repair aircraft. You can imagine things like doing virtual and physical co-simulation, staging robotic systems in industrial floor plants, maybe simpler applications like just navigation and asset tracking indoors. This last example here, remote expertise in telepresence, is also, I think, a pretty interesting area where the idea would be if you could do kind of photorealistic reality capture of spaces. And I know, again, this is something that robotics and the SLAM community has been pretty interested in, and then be able to have remote people that can basically go browse that 3D reconstruction of the space and perhaps even interact in real time with people locally that are wearing mixed reality headsets. So this kind of remote expertise, remote telepresence, some people call digital teleportation, as I think, one of these early sort of killer apps for mixed reality systems. And if you look at sort of the major platform trends that have changed computing over time, we've had things like mainframe computers, going to home computers, going to internet, the smartphone. A lot of people have speculated that mixed reality could be that next big platform change that reaches out a new set of users that currently, don't actually benefit from computers in their day job. I actually think there's a little bit more to this. So instead of just mixed reality, I think of it more in terms of what people often call spatial computing, where sort of at the bottom layer, you've got sensors and IoT, which are really taking physical content and creating a digital version of it. And then mixed reality is really allowing you to take digital and overlay onto physical. And again, this could be through a whole bunch of different modalities. Here's like mobile AR. Projection AR is another interesting way to think about augmented reality, where you have light projectors that project onto machinery. But really this synergy of both digital and physical coming together with the human in the loop, I think, is an extremely powerful concept. And a lot of these ideas around spatial computing sort of culminate in this common vision of having a shared view or set of channels where you have a bunch of different applications that come together in a single view. So like in this example, I don't know, somebody's walking through the airport, they have an app that's telling them about their gate information. They have I don't know, Yelp giving them food reviews that are customized. You might have an app for your company or your university that tells you if your colleagues are around. And people have been referring to this really as, a projection of the metaverse or AR cloud or digital twin. A term that has often been used for this is actually the spatial web. And kind of going back to the title of the talk, I want to focus in on why is this the web? What does the web actually have to do with any of this mixed reality discussion? And so maybe the best way to sort of explain that is to really look at what was the web actually designed to do before, obviously it's gone off in a whole bunch of different directions, but at its core, it's really about taking content, making that content something that's universally readable by a bunch of different platforms. And of course, the interpreters that we have for actually reading this content are web browsers. And then the rendering of the page changes depending on the platform and the context. So if we think about what the spatial web would be, we still need some way to represent content, but now we're also coupling that content with a live capture of the physical world. We also have, of course, platforms. Some of them are familiar to us, like laptops and phones. Some of them are perhaps new, like headsets. And of course, we have interpreters. And some of the major players in terms of interpreters are the same folks that are building normal web browsers, like we have the Mozillas and Chromes of the world. But you also have a couple of new players, like Oculus has their own browser. Mozilla has Firefox Reality, which is specifically a sort of a spatial web browser. And then the rendering actually looks very different depending on your context. So for example, if you're at a desktop machine, it might just be a 3D simulation that you're moving around in like a game. In VR, it's probably similar, but hopefully more immersive. You're actually inside a VR headset. But I think it gets really interesting when you think about augmented reality platforms, where that content is now actually linked to the physical world that's part of sort of the original construction. And just to give an example of what this looks like, and this is actually a preview of a platform that we've been building in the CONIX Research Center. So if I open up a regular spatial web page on a normal browser, it might look something like this, where I have, a 3D world that I can move around in. I've got buttons that I can click that are basically links. If I open that same view in Quest, it basically it looks similar. The difference here is, maybe you've got hands, you've got controllers, you can move around in the space. The interesting thing is then if I open this on something like the Microsoft HoloLens, I'm getting that same content, but anchored in the physical world. And in this context, this was sort of a pandemic photo that's in a living room. But ideally, this would be anchored to the place where this signage actually makes sense and has meaning in that particular environment. And then the hope would be that if you open it up in a mobile browser as well, you basically get that same sort of view. So we're really talking about this platform where you can develop your content, you can anchor it to physical reality, and you can just transparently view it from a whole different modalities and interfaces. And the reason why I think this would be interesting, at least for the robotics community, and I'll show some examples of this later, is that this is perhaps a really interesting and much more immersive way now for humans and robots to interact with each other, or even for development purposes, for you to be able to paint sort of debugging information into the environment. So instead of using, ROS-Viz on a desktop, imagine you had ROS-Viz where you could actually see that information overlaid in real time on the physical framework. And maybe one of the deeper things that's happening here is we're starting to see this as yet another driver for this sort of looming paradigm shift in the edge computing world. So right now, when people build kind of distributed applications or industrial IoT style applications, we've gotten really good at doing data management and machine learning in the cloud. We've gotten really sophisticated and powerful compute and actuation at the edge. We've seen a massive increase in sort of work in autonomous vehicles, robotics, speakers in your house that understand speech and can do Q&A. But if you think about how we program these systems, it's still very much sort of an up and down flow of data that's going from edge to cloud and back down. But in applications like, especially in autonomous systems like robotics, or in these sort of mixed reality, spatial web type applications where there's latency constraints and dynamics, this paradigm tends to break down. Oftentimes you don't have time to allow processing to go to the cloud. And so we imagine next generation platforms being much more about sort of this interconnect and being able to push computation where it needs to be within the network. And so a lot of the work that we're doing in the CONIX Research Center, as well as in just sort of spatial web in general, is thinking about how do we actually create the software architectures to enable these types of systems. And I'm probably preaching to the choir and talking about sort of the motivation of why mixed reality now. I mean, we've seen a lot of advances in depth sensing technologies. We've seen kind of the commoditization of things like ultra wideband ranging radios with the U1 chipset, making it into Apple phones. And so that technology has really progressed. This animation on the right is just ARKit doing basically visual inertial odometry and tracking. And it's accurate enough to the point where, you can actually walk out of a room, come back in with minimal enough drift that 3D objects still actually stay fixed in the same location. So it's the same SLAM technology from the robotics community, just sort of being applied into this graphical context. The other side of this that's happening is, of course, the miniaturization of wearables. We've seen some early prototypes of energy harvesting, single pixel contact lenses. There have been a whole variety of VR and AR headsets that have come to the market. People are speculating about the future Apple headsets, and you've got tons of these startups now that are working on sort of tightly integrated packages for inside the eye. So we have the sensors that are kind of there. We have people that are working on the platforms. I just came back from AWE last week, which is a augmented reality World Expo, saw a whole bunch of the new headsets that are sort of in the workflow. A lot of them are absolutely fantastic in terms of graphics fidelity, and they're starting to get better in terms of form factor. So it's all sort of coming together. The mixed reality community has also been working on, problems like registration, localization with pose, again, very central to robotics, scene understanding, figuring out surfaces, context, walls, occlusion, and building out sort of these platforms and wearables. So that's all rapidly improving. A lot of it, I think, has synergy back and forth with the robotics community. What's a little bit different in the spatial web context is really dealing with applications where you have multiple users that are interacting with each other, with the environment, where you have sort of these latency constraints. And so I have a number of these high-level challenges like programming and hosting applications, doing real-time interaction and sharing, doing real-time mapping and localization, reality capture, that I'm going to talk about a couple of clusters today with some of the sort of relevant work and projects that CONIX has been going on. So I'm going to start off by looking at this sort of problem of programming and hosting apps and dealing with real-time interactions. And on that front, we've been developing this platform, which we call ARENA, which stands for the Augmented Reality Edge Networking Architecture. And the idea here is that this is a platform we're designing to sort of simplify these mixed reality application development life cycles, where you can do things like location-based content discovery. If you walk into a space, you have something like a geographic DNS, like a domain name server, that you can pop up content that's near you, making sure that this is totally cross-platform. So that's something you get kind of from the web philosophy of designing systems, something that's programmable, implicitly networked. I'll get more to what that means. And then of course, safe and secure to begin with. So really trying to come up with what does that architecture look like for being able to have content and the real-time world mapped to all these different platforms. And so maybe a simple example walking through this platform that we've built is when you first come into a space, you might have users that are in a space. You obviously have some physical attributes in the space, like a table. And the first thing that you need to do is actually look up what content is near you. So we have a service, which we call the Atlas, which is this geographic domain server that connects you to a nearby edge computing platform that's hosting what we call realms that can host applications. And so what that kind of looks like is you make a connection to the system. It says, these are applications around you. Are you interested in any of them? If you select any of those applications, they launch and it kind of connects you to an edge compute system that's nearby. The assumption then is any users in the space have gone through that process, are connected to either one or many of these different embedded computers, which can then start to launch applications, in our case, these ARENA programs. And I'll get into this a little bit later. Our applications are actually based around WebAssembly, which is kind of a portable intermediate format that you can make a program so that it can run on a lot of different platforms. But the idea is these programs launch, and then if, for example, the program says, hey, I want to draw some graphical content in a space, it basically sends a message over a pub sub bus to any entity that's connected in the scene that says, hey, draw this message, draw this object at these locations. And then basically the client side software and all the different devices sees that message and draws the content. So for those that are familiar with X11 from back in the day, this is a very similar concept, right? We have basically a language that encapsulates the geometry information that anybody connected onto the network can sort of see and interpret. The other sort of interesting thing that's happening here is we're leveraging the organization of the pub sub in the scene graph within the scene to also encapsulate things like user IO and programs that are being launched. So you can think of this almost like a Unix file system abstraction where you have /proc/ et cetera, mixed with 3D graphics geometry. So the two are kind of put together, and kind of the best example of that would be if a user decides to, for example, click on an input. So for example, that chessboard showed up as a chessboard object in the scene. If the user clicks on it, that click message again becomes a pub sub message. It comes from the particular user, so people can actually see where that data is flowing from. And then of course the program can then say, oh, I'm going to respond to that by reacting and drawing a graphical element. And every sort of layer inside of this tree actually has the ability to have access controls applied to it. So you can control, who in a scene has the ability to create objects, to click on objects, to view objects, all of those types of fine-grained control. So here you see now it's drawn a circle, it's updated the scene graph on the side. So the interesting thing then happens is you can launch any number of other programs in the scene that could be launched either again at the embedded computer, or they could be launched on any of the clients. And those programs can similarly, if they have the right access privileges, manipulate this graphical tree, and they can actually start to draw their own content. So that same process can basically mix together any number of applications that people can interact with. So I want to sort of show an example of this through a video, which is sort of showing multiple applications interacting using mobile augmented reality. So here you see a regular, this is actually a prototype WebXR enabled browser that Mozilla built. It's finding content near it. I'm clicking on some application. You click on AR mode. In this case, it's relocalizing based on the April tag that's on the floor. So it's using sort of image-based processing to do relocalization. I'm going to talk later about other techniques we have for that. You notice that other users that are in the scene are implicitly also localized and network connected. So here's another user. You can actually see an avatar that's sort of floating over to denote their camera view in the scene. Sorry, I'm having trouble tracking my mouse here. This is an example of a program that's going to accept a click input, in this case, a navigation program, showing you kind of a path to follow. Here's an example of another program that's connected to the lighting infrastructure of the space. So you're clicking on that to control lighting. So this is kind of connected into a backend for interacting with digital infrastructure. And all of these are sort of, in this example, they're very simple Python programs that are being hosted and run independently, but mixed together into this common operating framework. Literally, here's an example of launching like a simple tic-tac-toe program coming out of Raspberry Pi. Of course, it dramatically appears because it's XR, but you basically get all of this sort of implicit networking and connectivity for free. So there's nothing special you have to do to write a tic-tac-toe program for it to interact across multiple people. And you can see a couple of hints of real world capture of the geometric surfaces, like the blocks, they actually fall off the table. So that's something that's sort of populated in the world view in the back end. And then you can imagine being able to relocalize across different markers and sort of scale as you go. And this is, again, another instance of that program. So that shows kind of an example of what we mean by this sort of spatial web architecture and how these components can come together. And so to dive a little bit more deeply into the architecture, we're starting off with this atlas. It's connecting you with a realm. Underneath the hood, this is basically the realm is basically providing an HTTP endpoint. So basically pushing out the content of models and programs, et cetera, over REST. We have a pub sub interface, which is actually sort of a modified version of MQTT that we're running. There's a bunch of services that pop up with things like, persistent data storage, something that tracks the state of a scene and can provide you with updates, a runtime supervisor. We also have, of course, the client stack that runs on the viewer devices. So this is where we're actually building off of WebXR and A-Frame and 3.js. Basically, there's sort of a well-defined web stack for doing 3D graphics in a cross-platform manner. What we're bringing in is the connectivity and things like the relocalization and sort of all of the glue that stitches it together. And then we have these Arena runtime components, which allow you to run the different programs. And basically every host entity that connects into the system can actually run programs based on, again, access control and permissions, but by default can run programs that the system basically dispatches. So whenever anything connects to the system, they're actually providing compute resources that can be used to execute other programs. And then we, of course, have provisions for sort of headless devices. Like in this case, if you wanted to run something on an IoT widget or a robotic component, you could actually just have sort of a headless Linux-based runtime. So to go a little bit under the hood, this is a example where I've got two browser windows that are open. I've got two terminal windows that are open. This is kind of a quick view of what some of the Python code looks like. I'm basically going to run at the command line a Python program that would try to draw some geometry into these scenes. It, of course, asks you to authenticate. So we use OAuth to pull down a token based on that user's access control privileges. So this program is now running as that user that connected. And what you can see is it's drawing boxes that are appearing in sync between the two different browser windows. And as you move around in the browser windows, you can sort of see different views into the scene. I think this was actually supposed to show some security stuff. So it's showing an example of what some of our JWT tokens look like. That's probably too much detail for a talk like this, but I think it's just important to note that this whole scene geometry graph has access control and permissions behind the scenes. More importantly, you'll see that, in the bottom window now, we're running another Python program, and that is then overlaid into that same view. So that's sort of how these mixed applications would look. And I think the important thing to remember is that this all also happens in augmented reality as well. So this is kind of that same program that's running, but you're seeing sort of the augmented reality view of it. Here's another example that kind of drives that point home a little bit more specifically, which is two windows in the upper left and the bottom. The upper and lower windows on the left are sort of AR views from two different users. The right hand side is the VR interpretation of the environment. And you can actually see two users that are running a program in the environment that's allowing them to build and sort of author the space. And you can get a sense for the fact that, we're rebuilding a lot of sort of standard operating system components that need to exist in the spatial world. Like here is that display that the person is using to select and to create an author. That again is just ends up just being a program. Oh, that's nice. Talk about a user interface glitch in PowerPoint. All right, get rid of the pointer. So you're kind of able to place, change, manipulate geometry. And because of this sort of network transparency and the implicit networking that's happening, this is again all sort of hidden from the developer and made pretty easy and controllable. So, having this capability is great, but it kind of brings up the question of what should a spatial computing runtime that supports applications in this context really look like. And we know, if you go back to sort of our original figure, we know we've got some interactions at the edge that are happening in the order of milliseconds. We've got some interactions out to the cloud that could be 20 milliseconds or greater. And sort of our hypothesis here is that the best approach to programming these types of systems should really be built around distribution, security, and timeliness as sort of first order primitives. And so what a bunch of folks in the CONIX Research Center have been doing is building out this abstraction, which we call, and I believe the term was coined actually by Mozilla, this notion of a nano process. And so the idea is that a nano process is a lightweight computational abstraction. So it looks something like a small program that can basically execute on its own, that's in a protected context. So if you think about current programs and paradigms that we use to run either serverless or Kubernetes style orchestrated computations, the point of isolation is usually either a process or a container. So a container being larger, holding a bunch of processes, a process being kind of the OS abstraction. This is something actually smaller. So the idea is that these execution contexts can be basically almost like single threads, but they're completely protected. They also have very explicit interdependency. So all of the libraries that they make calls from and all the interfaces are actually very controlled, which makes it much easier to sort of monitor, instantiate, and sort of manage all of the resources coming in and out of it. And so a collection of these modules would then be pulled together to sort of build an application. And the idea is that this is really focused first and foremost on security, sandboxing, and isolation from the start. And so if you think about this in terms of something that's lighter than even a even a process, certainly much lighter than a container. You can imagine being able to run, tens of thousands of these things and spin them up and down very, very quickly, but they can also keep state. So it's not quite like a Lambda function for people that are familiar with serverless, where it's a one-shot thing. This could actually be long running programs. And it turns out that looking through the sort of space of technologies right now that exist, this maps extremely nicely to something called WebAssembly. And so WebAssembly is basically this intermediate instruction set format and execution context that the web community built to basically try to run these types of threads in the web. And again, since of course the web is sort of one of the worst security environments that you can face, built specifically around sort of sandboxing and actually also relatively high performance. And so the idea is that we use WebAssembly built in these sandboxes to run our different execution components. And right now, WebAssembly is actually standard in all web browsers. So that means not just a desktop browser, but also your mobile phone can run WebAssembly, which is part of how we can very easily have any client that connects be able to host our own runtimes. But we're also starting to see a lot of adoption outside of the web. So for example, in Internet of Things, Intel has an effort called WAMR to build kind of small, very lightweight WebAssembly things in content delivery networks and CDNs, Fastly, Cloudflare. They're all using, again, WebAssembly as kind of a base technology. And one of the really cool things about WebAssembly is you can run it interpreted, you can run it ahead of time compiled. So you can take WebAssembly, you can compile it into raw machine level assembly and still actually keep the memory protection and properties from the original WebAssembly program. There's a lot of folks working on sort of provable ways to do that with compilers. And you can also do just-in-time compilation. So the idea is that sort of these nano processes become this nice abstraction for how we can execute programs. And if you look at sort of the general trend and evolution from embedded systems, where you start off with very specialized hardware systems where you've got an RTOS, domain-specific software, and it's going through a certification process. As it becomes more commoditized, you start to say, okay, well, I'd like to bring in third-party components that maybe are not going through certification, to the point where you start to say, hey, I'm not going to do certification anymore. I'm going to connect things to the internet. And this is really where you absolutely want something more like a WebAssembly type framework to actually support these types of applications. So I think that it's obviously an interesting option for the spatial web space. We're seeing it for other applications. I think this actually could be a very interesting paradigm also for sort of distributed robotics style systems. I can imagine something like ROS2 perhaps supporting the ability to have safe and controlled modules built around this. And not going to go into a lot of details, but we have a bunch of work around how to actually manage, monitor, and run these types of components. So this would be almost like the Kubernetes for some of our WebAssembly work. And the takeaway is that there is a bit of a difference in how you manage a cloud infrastructure where you have a very homogeneous, well-connected system versus something where you've got components that are sort of spanning the edge. And one of the big differences is actually the connectivity and trying to understand the spatial requirements of different applications. So this whole arena infrastructure is actually something that's completely open source. It's available on the web. If you go to arenaxr.org, you can kind of drop in and actually test it. You can also go to the GitHub page. We've been in the process of scaling it a bit. So within the CONIX Research Center, we've been creating a network of arena servers to build out kind of this larger infrastructure where you can locally host and run applications and content, but then easily share that across a wider network across the different universities in CONIX. And then actually when the pandemic hit, one thing that we decided to add was the ability to add Telepresence Extensions. So we added a sort of an AV server so that you could actually stream video. You could go into 3D scenes and actually project video as well as spatial audio. So you can actually hear where audio is coming from. And so this is kind of a snapshot of this web interface where you can kind of see, it's almost like many of these sort of weird telepresence things that have popped up in the pandemic, although ours actually was built on top of an architecture that made this pretty easy and scalable. And so one kind of interesting example that came out of this is actually a project that was made by Paulo Tobueda's lab at UCLA. So he works on sort of data-driven control. And here he has, small crazy fly that's flying around. On the right side, you can see a mirror of it in the arena. And so they were demonstrating at a CONIX annual review some of their technology and some of the data-driven control that they were doing. But what you can see is that people from all over the country were able to connect into this interactive scene and turn on video and actually talk to each other and point things out. And you could see that they projected sort of video images of their labs, their poster content around. So they basically created this immersive 3D environment where we could all kind of look at the project, discuss, point it out, but really see this real-time physical interaction. It was this really sort of interesting experience where you actually felt like, yes, I'm actually, almost seeing a real demo in a lab, to crawl some of that back. So it's interesting to see sort of the social component pulled into the system. We also, just to kind of give a sense of how hard it is to develop, we had an undergrad that said, okay, let's do some robotic visualization stuff. And so this was like a very simple thing through an iPad where they said, okay, they're using their rover to do whatever path planning they were doing for a course, but you could actually overlay the sensor data and sort of the view from the robot very, very easily using the arena infrastructure. So I want to sort of shift gears and talk a little bit about some of the localization and mapping work that's behind the scenes. And for the most part, most of the localization that we've been looking at is either feature-based with LiDAR and images from a phone or a tablet, or range-based localization. And so when we first started off, we were basically in the world where we were doing sort of fixed infrastructure where you had beacons at known points. For those of you that have used ultra wideband, you're probably familiar with, taking something like POSI XYZ, metering out the location. Next, we looked at sort of automatic mapping. So can you do range only SLAM? And then most recently, we've been looking at basically, completely relative positioning. So what happens if you have a range only SLAM problem that's mobile, where you don't necessarily care about anchoring it into a physical, into a single coordinate system, which is actually for augmented reality, all you really need. So we built a number of sort of hardware prototypes. These are different generations of things like beacons and access points. Here's sort of an example of an IMU, an ultra wideband radio, like a little Pi Zero connected together. We moved more towards a Pi and T265 type solution. Now with Intel getting rid of the T265, we're doing onboard vision processing on the Pi to get rid of that. But just to show like a little bit of the evolution. So our first versions, you could see sort of small baseline UWB transceivers with a couple of students walking around with mobile phone devices. So this is using UWB and then VIO coming from ARKit. And you can actually see the tracking performance is pretty decent. One of my students, Naranjani, she's going to walk up the spiral stairs. This is Newell Simon Hall at CMU, which is actually where a lot of the Robotics Institute lives. So you can see sort of tracking with a fixed baseline. So when that got working pretty well, we looked at doing range only SLAM. Let's see if this is starting to play. So here's kind of an example where we developed a open source firmware package for the DecaWave evaluation modules, these beacons. So you can basically flash these beacons with some code. You can use AT commands to set just their MAC address, and then you can walk around with a mobile phone through the space. It's tracking its position with VIO and then also doing UWB ranging, and then it will actually localize all the beacons and then show you sort of the localization in augmented reality. So you can actually sanity check to see how well it's aligned. And this actually is something that you can buy these on DigiKey. You can grab the source from our website. You can load it up and you can actually see like a pretty nice UWB SLAM mapping environment. So then we kind of looked at the next challenge, which was, can we do completely relative localization? So here, kind of our goal was not just to be able to do sort of network localization where you've got common shared features, but be able to also map with some agents in the system that were not even in line of sight or seeing any of the shared features from any of the other agents. So you basically have an inertial trajectory, you've got, opportunistic pairwise ranging. Can you actually pull that together and solve the network localization problem in real time? And so, of course, this kind of comes down to the fact that if you've got these devices, if they've got trajectories, you really just need to figure out how to align the trajectories over time. We've looked at a couple of different approaches for this. This is an example of a particle filter-based approach. We've also looked at factor graph-based approaches. They perform actually similarly. It doesn't seem like there was a huge gain. But you can see that basically as you move, especially if you get relatively near the other agents, you can get a pretty decent confidence on the relative location between the different agents. And so the fun thing is taking this algorithm and then deploying that on Arena. You can actually see the performance in real time in augmented reality, again, going across platforms. So these are all devices that have ultra wideband transceivers in them, and you can basically see real-time mapping. So you're seeing this through an iPad, which is actually how we're recording the screen. Then you'll see an example of like multiple agents. These are all different that are moving through the space. So again, they don't necessarily know where they are in absolute space, but they know their relative local location enough that they can actually do the augmented reality overlay. So we definitely thought this was a promising direction. One thing that my group, coming from its RF sensing background, realized is that visual inertial odometry certainly has limitations. And so one thing that we've been looking at is what can we do with chip scale millimeter wave radar systems? And if you kind of look at the traditional processing pipeline that people use with radar, they try to apply something like a CFAR processing step where they really reduce the data down to, something that looks like the heavy reflector points. But if you look at what a lot of these chips are producing, you have all of this great high rate information of raw IQ data, which is kind of sharing both amplitude and phase from the radar coming back, that could be a whole lot richer. And unfortunately, it's tough to deal with. It's very high data rate. It's between 600 megabits per second to 2.4 gigabits per second, depending on how big your radar array is. It's really noisy. It's often environmentally dependent. And actually, to extract the best performance, you often need to change the antenna geometry. A lot of these systems are designed for collision avoidance in cars, whereas if you want to do something like localization and mapping, you probably want a much wider field of view. And so we've basically been looking at taking raw IQ data from millimeter wave radar, sort of ground truthing it with a mobile LiDAR unit and looking at different processing pipelines and RF processing chains to see if we can extract some of that inertial measurement data out. And this is actually a paper by some colleagues of mine, Nikki Trigoni and Andrew Merkham, where they did some initial work on basically using millimeter wave radar to do sort of 6DoF SLAM. But it turns out, there's a lot of work that still needs to go into understanding this processing pipeline here. And so some of the latest work that we've been doing is looking at, can we actually take millimeter wave data and get sort of LiDAR level SLAM and localization out of it? Unfortunately, we don't have results quite yet. I can tell you some of the stuff that's cooking is actually quite promising. So hopefully you'll hear something from us soon, but definitely a lot of interesting work to be done in this space. The other thing that we've been looking at, where we do actually have a paper from this last year, actually MobiCon 21, that looked at saying, okay, well, if we have these millimeter wave radars that are trying to do localization and mapping, can we make optical markers? Can we make like the April tag equivalent in the RF domain that could be used as a beacon and an anchor? And so my former postdoc, who actually just started now at UIUC, Alahe Saltaganai, she has been working on retroreflective backscatter low power markers. And so the idea here is that you can sort of modulate these millimeter wave antennas by basically switching them on and off at a known frequency to act as an active reflector. And sort of the short version of the paper and the work is that yes, you can actually detect them very easily if you encode them, and they can actually get sort of fantastic range performance, like, hundreds, almost up to 200 meters with the sort of commodity vehicular radar that you can get from Texas Instruments. And we can do this in 3D space. So here's an example of that system connected to Arena that is doing multiple object tracking. So these are multiple retroreflectors, and you can see sort of how they're being tracked. And probably the more impressive demonstration here is tracking a single object, but this object is actually behind a wall. And I apologize, this is like a really choppy video, early rough cut, but you get the idea. So you can actually see, at least penetrate through some material, especially if that tag is actually heavily coded. And I think in the interest of time, I'll probably skip through some of this, but we have other work that's been using like visual light communication techniques to try to localize and identify points to bring up user interfaces and to act as AR anchors. This was actually a piece of work from just this last year where we looked at basically taking active quads that are inside a video frame feed, where you could take existing video, put what we call flash anchors in, and then basically build a really simple low compute tracker that you can actually even run within a web browser. On the right side, this is a web browser that's running this. That gives you, we were seeing around 35% more range than April tags, the ability to operate at a much sharper angle. And of course, since they're active, they work in the dark. It's like a backlit April tag. So some interesting technology is sort of built around the localization and tracking that I think could be interesting crossovers, again, to the robotics community. And the last sort of section I want to talk about is some of the work that we've done with reality capture. And this is really just tying a bunch of these components together. But ISMAR, which is kind of one of the premier mixed reality conferences, they had a competition this year for who could create the best hybrid experience for a remote and in-person conference. And so for that, we actually took a scan of our lab, and we had basically a bunch of features that we added into it using the Arena, like the ability to screen share. We had some portals which had cameras, and they were basically double-sided monitors that had cameras in both ways, where people in the real world could look through and see people in the virtual world, and people in the virtual world could look through and see people in the real world, and they could also talk with sort of spatial audio. And here's kind of a very quick demo video of kind of what that looks like. So we scan the venue first with the terrestrial LiDAR system to get the sort of 3D geometry. This is a VR person walking through a space in CMU. This is an AR person that can actually see and then, of course, interact in AV with the virtual person. Here's an example of a magic leap with a front-facing camera that basically overlays a speaker view on top of it. And so in AR, it looks a little bit weird because you normally wouldn't show the person, but when that person looks out in the crowd, they can actually see sort of all of the digital people. And then this is kind of an example of one of those portals that allows you to look back and forth between the real world and the digital world, so you can have interactions there. And again, all with sort of spatial audio. And maybe just to hone in on the digital portal side, here's kind of an example of a demo where Ivan is walking through. You can see him from the VR side. And then if you go to the other side of the portal, you can again see him on that side. And note that he's getting his video feed and all of the tracking information just from the mobile phone that he's carrying through the space. I think I'm going to skip this video for now. This is some work that Ramesh Govind's group has done at USC on multi-LiDAR stitching stuff. So basically, in summary, we've been developing this Arena platform. I think it's a really sort of interesting platform that could be used at, the intersection of mixed reality and perhaps robotic or IoT style systems. It's really focused on the distributed compute properties of these types of systems, as well as kind of security and isolation. Again, I'd highly recommend jumping in and checking it out. You can actually just go in through your web browser, log in and be able to explore some 3D scenes. We have a couple of public ones that are available. And again, documentation, code, all that good stuff is all there. And I actually want to especially thank the Arena team that works on this, like Nuno Pereira, Mike Farb, Ivan Lang, Eric Kriebling, and Edward Liu. It's a great mixture of research programmers and students coming together to really build out something that I think is pretty awesome and cool. And I also want to thank all of the folks in CONIX. Here's the list of sort of PIs, so 22 PIs across 6 different universities. They're all working on, many different elements that come together, and we use Arena as kind of our integrator platform, but they're obviously all sort of specialized in other different subcomponents. So cool. Looks like I'm a minute or two over. So with that, I would be happy to take any questions.
Okay. If anybody has any questions, you can just unmute yourself and ask away.
Hey, Professor Rowe, thank you for the presentation. It's really an impressive amount of infrastructure work and getting things working and demos. So coming from kind of the robotics perspective, something that we've thought about, and I would admit here quite primitively in comparison to what you've shown here, is kind of mixed reality experiments and trying to meld physical robot spaces with what we do in simulation, which largely remain kind of partitioned.
Yep.
And so I'm curious from your perspective, what technological advances need to happen for things like mixed reality robot labs to become more commonplace, more easy to use, or if in fact you think it just requires a bit of programming effort.
I think conceptually, especially if you're talking about robotic labs, I mean, you have the ability to do a lot of instrumentation locally. You guys could put up optical tracking systems, which kind of circumvent a lot of the localization challenges that people would have in the wild. So I think in the lab context, this type of stuff is doable today. I think some of the biggest challenges, though, are still around if you're doing reality capture, then you need to start thinking about modeling things like physics, which, as we know, gets arbitrarily complex. It turns out that distributed physics is even harder. Like a lot of gaming engines, they still sort of work towards a centralized arbitrator that makes all of the decisions. And that's, of course, less scalable. But I think, in the lab context, especially if you think of a place like Penn or CMU, the basic technology components are probably there that you could do a pretty good sort of robotic digital twin style lab. That being said, there is definitely a lot of elbow grease that would have to go into it. I mean, we've been working on Arena for a number of years, getting things like security actually worked out is pretty challenging. So if you're okay making some shortcuts there, definitely doable, but longer vision of like, let's say you wanted to make a platform that you could copy and paste across all universities in the country, or you're trying to create a big sort of distributed digital twin robotics lab, then I think you have to face all of these sort of infrastructure scaling pains. I'd be curious actually what type of what type of mixed reality work in robotics that you guys are actually doing?
So it isn't a lot, but folks have thought about how can we run experiments where we only can afford perhaps to buy or maintain 2 robots, but we want to show a demonstration with 5.
I
and
see.
so you have an experiment space where you're running your 2 robots, and then you're simulating additional agents, and you're kind of bringing all of that together into one kind of cohesive demonstration that somehow you can weave together into a video or something,
Yep.
and show to people.
Yeah. So I mean, that's hopefully you got a sense of it from some of our videos, but one of the really powerful things, at least with WebXR and having these cross-platform capabilities, is that being able to just use a regular iPad as your virtual camera is extremely powerful. Like, you can basically walk through a scene and you get the ROS Viz data on top of the real world live, which I think was really cool for some of, for example, Paolo's students to be able to easily do. But yeah, no, I could definitely see the power of that. And I also realized, looking at whenever you watch the well-produced sort of Boston Dynamics style videos, you're like, oh yeah, robots are perfect. They just run like this all the time. And then you see like the behind the scenes of, no, it took us 26 runs to actually get these, 3 robots to play well together. So yeah, I think a lot of people don't realize how much goes into actually getting these systems up and running still. So.
Yeah. As someone who's done a little bit of infrastructure work myself, anytime I see videos and you had dozens of them, it is really impressive how much work goes into all of that.
Cool. Yeah. But I think I don't know if I really answered your question. I technically doable, but we're still, I think there's still a fair bit of development that needs to happen before it's turnkey and easy.
Yeah, I think, having or reaching a state, and we think about this even from the robotics perspective of having capabilities that are turnkey and easy, so that not everyone has to start from scratch when they're trying to run an experiment and implement localization and implement a planner. And sadly, I think we still are kind of at a state where a lot of that does happen. But it would be really nice. So, I'm seeing in some of the demos that you're showing, connecting to a kind of commodity off the shelf capabilities, whether that's the localization capability that's offered by your iPad or other kind of sensors that are available. And that excites me about kind of making that reality in a robotic setting where not everyone has to be implementing everything from scratch themselves, but you can kind of walk into a space and utilize robots and capabilities more free form.
I mean, I feel like that's partially sort of the dream of Ross. Like, Ross has made some steps in the right direction, although I guess still room for improvement, obviously. But yeah. No, it's definitely interesting. I mean, the good news is, at least coming from the headset world, as well as like a lot of the work that Microsoft has done with the latest versions of Kinect, like, we've gotten sensors that are now getting pretty good at kind of localization, relocalization, and tracking, and kind of exposing that in an easy way, which I think has always been one of the nasty challenges. You guys, of course, have that whole mechanical subsystem as well that I think is also equally, if not more, challenging. So
yeah, I don't want to steal all the time. So if anyone has other questions that they want to ask, I do have one more that I would like to ask if there's time. What's up, Carl? I'm not able to hear you.
There's no one else in line to ask questions.
Okay. Yeah. Also, I mean, as you're developing systems that mix so many different technological modalities, you have to, put on a lot of different hats. And I think one in AR and VR is like human robot interaction, or human machine interaction. And I'm wondering if you have any advice, for people who come very much from the technological side of things, of developing algorithms and robots, essentially, who are now, also trying to do HRI and visualization. And what advice do you have there?
Reach out to an HCI colleague. Yeah, don't reinvent the wheel, right? Actually, there's plenty of HCI people that would love to pair up with roboticists. And I know, for example, Claire Tomlin at Berkeley, like she was working in a group that was definitely looking at sort of robot human interaction, also with augmented reality. And I definitely see that happening a fair bit at CMU. But yeah, I would say, find somebody in the HCI community that's interested in that. And yeah, don't I guess occasionally if you're coming from an outside community, you come in with a different perspective and maybe that leads to a breakthrough. But there's been so much work done in sort of HCI and mixed reality interfaces and design that I think it makes the most sense to sort of pair up with somebody else in that space and just sort of amplify each other's efforts.
Yeah. Well, I appreciate the talk. It's very interesting. And I am someone who kind of works kind of fully in simulation. I think in robotics right now, people are really devoting a lot of effort to building simulators. But, I see long down the road, some of these capabilities that exist now fully in simulation could start migrating to more AR, VR type context. So this is very exciting from that perspective.
I look forward to that day, and we've definitely been thinking more and more about like the right way to connect some of the mixed reality work with robotics to sort of make that easier for people to develop on. And it's kind of interesting. You may end up seeing a mashup of, I don't know, Unity, Unreal platforms, and then even, robotics type infrastructure coming together at some point, hopefully soon.
Yeah. Yep. All right. I have to run. Thanks so much.
Cool. Anyway, thanks a lot, guys. Thanks, Carl.
Thank you.